Hi everybody, today we're going to walk you through two different methods of approximation that involve derivatives, linearization and differentials. We'll start first with linear approximations and then move on to differentials. So as you can see on the screen here, I've drawn a diagram of the function g of x is equal to the square root of x, and I've labeled the point on here x is equal to 4. So what if I'm trying to find a value on this function? For example, g of 3.99. If I had a calculator, it wouldn't be that hard to plug in 3.99 to my function and just have it spit out an answer. But if I didn't have a calculator around, that would be pretty nasty. But if you notice here on this diagram, I've drawn a tangent line to the point x equals 4 on this function. And the value of y on the tangent line at 3.99 is actually very similar to the value of the function itself at 3.99. And I'll label that point here. So this will hold true as long as you stay near the original value, which is x equals 4. So this is kind of where linear approximations come in. We can actually use the tangent line of a function at a particular point to approximate the values of the function near that point. So for example, we have the line tangent to the function at the point x is equal to 4, y is equal to 2. And we can use that tangent line to approximate values like g of 3.99, g of 3.95, g of 4.1, etc. So linear approximations are very useful in estimating values of functions when you don't have a calculator. So to calculate linear approximations, you'll use the formula L of x is equal to f of a plus f prime of a times x minus a. So this formula might look unfamiliar in some aspects, but don't be worried. Throughout this course, we've been using derivatives to find the equations of the line tangent to a function at a specific point using this formula. Y minus y1 is equal to m times x minus x1. And so this linearization formula up here is just a reconfiguration of the tangent line equation. So now let's work through some example problems so I can illustrate this concept in practice. So example 1. Find the linearization of the function f of x is equal to x cubed at a is equal to 2. Use it to estimate f of 2.1. And so I've gone ahead and written the linearization formula on the screen already. Okay, so let's look at what we have and what we need to find. We have a is equal to 2. And so that means that f of a is equal to 2 cubed, which is equal to 8. And so now we need to find f prime of a. So let's start with f of x is equal to x cubed. That means that f prime of x is equal to 3x squared, and that f prime of a is equal to f prime of 2, which is equal to 3 times 2 squared, which is equal to 3 times 4, and we finally get 12. So now let's plug in what we have. L of x is equal to 8 plus 12 times x minus a, which is 2. So we've gone ahead and we have linearized this function. So now let's use it to estimate 2.1. So x is equal to 2.1, and so if we want to estimate this, all we have to do is plug x into our linearization formula here. So L of 2.1 is equal to 8 plus 12 times 2.1 minus 2. And that's going to be equal to 8 plus 12 times 1 over 10. So that's going to be equal to 8 plus 1.2, and ultimately we get 9.2. So there's an example of how we can use linearization to approximate the value of this function. Now let's check our work here. Let's check what happens when we use a calculator to find the value, the actual value of 2.1 cubed. So when we do that, we get 9.261. 1. So as you can see, this value gets, this linearization process gets us pretty close to the actual value. Okay, so let's try another example. Now they're asking us to approximate the value of the square root of 37. And so this example is a little bit different from the previous one in that we're not given f of x, we're not given the value of a, and so we kind of have to discern those for ourselves. So just looking at this expression right here, I'm going to create my f of x, and I'm going to make it the square root of x. And so that means that x in this scenario would be equal to 37. So now we need to find our a, our f of a, and f prime of a. So a is going to be a value that we choose here that has to be close to this x, and that will help us approximate the function. And it needs to be something that we know how to deal with. And so looking at this, what instantly comes to mind is setting a equal to 36, because we know what the square root of 36 is. It's 6, so having that known value makes this process easier for us. So if a is 36, f of a is equal to the square root of 36, which is equal to 6, and let's calculate f prime of a. So f prime of x is equal to 1/2 x to the negative 1/2, which is equal to 1 over 2 square root x. And so now if we plug in 36, so we plug in a, we get 1 over 2 times the square root of 36, which is 1 over 12. Sorry about that. That should be f prime of 36. Okay. So now we have f of a, f prime of a, and a. And so we can just plug these values into our linearization formula. So we get L of x is equal to f of a, which is 6, plus f prime of a, which is 1 over 12, times x minus a, which is 36. Okay. So now our final step would be to approximate the square root of 37. So we're going to plug in 37 to this function right here, where x is. So L of 37 is equal to 6 plus 1 over 12 times 37 minus 36. And that's going to be equal to 6 plus 1 over 12 times 1. And that is going to be equal to 72 over 12 plus 1 over 12. And finally we get 73 over 12. So now, again, let's check our work and calculate the square root of 37 just using a calculator. And that gets us 6.08276. And so if I divide 73 by 12, which is what we got through our linearization, I get 6.083 forever, 3333. And so as you can see, this once again is a pretty good approximation of the actual value of the square root of 37. Okay, let's try one last example before we move on from linearization. So they're asking us to find the linear approximation of f of x is equal to x sine of pi x squared at a equals 2, and to use that approximation to estimate f of 1.99. So I've gone ahead and written down our linearization formula right here. And so let's see, we've already got a is equal to 2. They've given that to us. And so our next step would be to find f of a. Oh, sorry about that. F of 2 is going to be equal to 2 times sine of 4 pi. And that's going to be equal to 2 times 0. And so we'll get 0 for that value. And now we need to find f prime of a. And that's going to be a little bit more complicated because we have a product rule and we have a chain rule. So we have f of x is equal to x times sine pi x squared. Wonderful. And so we have one function here and another function here. And within that function, we need to use the chain rule. So I won't go into the whole process of finding f prime of x in this video, just for the sake of time here. But essentially, I put f prime of x on the screen here. And so if we plug in 2 for f prime of a, we get 8 pi. Okay, so now let's plug everything into our linearization formula. L of x is equal to f of a, which is 0, plus f prime of a, 8 pi, times x minus a, which is 2. And so now if we are approximating the value of 1.99, we get L of 1.99 is equal to 8 pi times 1.99 minus 2, and that's going to give us 8 pi times negative 0.01, 0.08 pi. There we go. Okay. And as always, you can check your work by calculating the actual value of f of 1.99 using a calculator and comparing that to the value here that you get through linear approximation. So if we actually do use a calculator to figure out what f of 1.99 is, we get negative 0.248 to 3 decimal places. And if we simplify this value here, we get negative 0.251. So the value we obtained through linearization is negative 0.251, and the actual value of the function would be negative 0.248. So as you can see, we get a pretty close approximation using this process. Okay, so now let's recap what we've learned about linearization. So linearization is a method for approximation that uses derivatives and tangent lines. And the closer you remain to the point that you linearized at, the better your approximation will be. Okay, so now let's move on to differentials. Differentials are essentially another way of looking at a very similar concept, and what they allow us to do is approximate the change in y, or delta y, from one point to another. Differentials are very closely related to derivatives, and they can help us look at the change in quantities in a function. So, for example, if you had y is equal to f of x, and you took the derivative of both sides, you'd get y prime is equal to f prime of x. And we know that another way to represent y prime is dy over dx. dy is the differential of y. So if you were asked to find the differential of y here, all you'd have to do is multiply dx by both sides. And that would leave you with dy is equal to f prime of x times dx. So this is the process we're going to be using to find differentials of y later on. Okay, so how are differentials useful tools for approximations? So I've drawn a sketch here of, once again, the square root of x. And I've got 2 points on here, 4, 2, and 9, 3. Okay. So if I draw this little triangle here, this segment right here would be delta x, and this segment right here would be delta y. So the change in x on the function between these 2 points and the change in y on the function between these 2 points. And so how would I calculate delta x and delta y? Well, delta x is pretty simple. So between these 2 points, we've got 9 minus 4 equals 5. So the change in x over these 2 points is 5. And now let's look at the change in y. So we go from 3 to 2, and that gives us 1. Okay, so it's pretty simple to calculate the change in y and the change in x when you've got really nice numbers like 4 and 2 and 9 and 3. But what if, once again, we didn't have a calculator and we had some more gnarly numbers? So I've redrawn this function here, and we've got, once again, the point 4, 2. And now we've also got a different point, which is 5 square root 5. Okay. And notice that I've also drawn a tangent line to the function at this point, x is equal to 4. And that's depicted in orange. So let's calculate delta x. Delta x is once again pretty simple. We've got 5 minus 4 is equal to 1. And delta y, that would be equal to the square root of 5 minus 2. Okay, so if I wanted to simplify this a little bit further from here, but I did not have a calculator, it would be kind of difficult. So that's where dx and dy can kind of come into play. So how do dx and dy relate to delta x and delta y? Well, delta x is just going to be equal to dx. So our differential of x is going to be equal to the change in x, but this doesn't hold true for delta y. dy is only going to serve as an approximation for delta y. And on this function, this is going to be dy, the segment that I've just drawn in orange. So as you can see, they are not the same. And that's because dy is associated with this tangent line here, rather than with the function itself. So how are we going to calculate dy? Well, what we need is the derivative of the function. So we have f of x is equal to x to the 1/2, which means that f prime of x, or dy over dx, is going to be equal to 1 over 2 square root x. Now if we multiply both sides by dx, as I showed you before, we get dy is equal to 1 over 2 root x times dx. And now let's plug in 4 here. dy is equal to 1 over 2 times the square root of 4 times dx. And we know what our dx is. We just calculated it. So that would be 1. And that means that dy is equal to 1 over 2 times 2, which is equal to 1 over 4. So basically, that is an approximation of the change in y on the function between these 2 points, 4 and 5. And so if we started at the point 4 with a y value of 2, we should add 1/4, or 0.25, which is our differential estimate, to get 2.25 at the point 5. And so if we actually calculate the square root of 5, we get the value 2.236. So once again, a pretty good estimate. So if you're still having some trouble understanding the connection between delta y and dy and delta x and dx, you can look at this diagram that I've pulled from the textbook here. And so I've got the function y is equal to f of x labeled here in red, and there's points p and q on that function. And then I've got a tangent line to the function at point p, and that is labeled in green. And I've also got these two x values labeled down here at the bottom, x and x plus delta x. So I've got delta x and delta y labeled here, just as we talked about before. And so if we're looking at what dy and dx are, we have to look at the tangent line. So we know that delta x is equal to dx, but delta y is not equal to dy. dy on this function would be equal to this segment right here, because it's associated with the tangent line. And so as you can see, this provides us an estimation as I mentioned before, of delta y rather than the actual delta y itself. If we wanted to actually find the real value of delta y, we'd have to use the following formula. Delta y is equal to f of x plus delta x. So that's just this x value right here, minus f of x. And so this formula right here is going to be important for problems that we will do shortly. Okay, so let's move on to some examples that will allow us to practice with differentials. So they're asking us to find the differential of y for the function y is equal to x to the 6th plus 7x squared plus 3x. And so essentially what they're asking us to find is dy. So let's take the derivative of both sides of this equation. That gives us dy over dx is equal to 6x to the 5th plus 14x plus 3. And now if we multiply both sides by dx, that leaves us with dy is equal to 6x to the 5th plus 14x plus 3 times dx. And that's it. We found the differential of y. Okay, so let's move on to our second example for differentials. And so in this problem, they're asking us to find the differential of y for the function y is equal to x squared ln x. And so for this problem, we're going to have to use the product rule. We've got our first function here, and we've got our second function here. So we've got y is equal to h of x times g of x, and this is just me carrying out the product rule right now. And we're going to set x squared equal to h of x and ln x equal to g of x. And h prime of x is equal to 2x, and g prime of x is equal to 1 over x. So we know that dy over dx is going to be equal to h prime of x times g of x plus g prime of x times h of x. And this here is just the product rule. Okay. And so now let's plug everything in. Dy over dx is equal to 2x ln x plus x squared over x. And let's multiply both sides by dx. And so that leaves us with dy is equal to 2x ln x plus x all multiplied by dx. Okay, so let's move on to our third and final example for differentials. And this problem is slightly different because we're given new pieces of information. So in this problem, they're asking us to find dy and delta y for the function y is equal to x cubed and compare them. And they're giving us these two new pieces of information, delta x and x. So let's just start by doing the same process that we have been doing for the other problems. Y is equal to x cubed, that means dy over dx is equal to 3x squared, and that means that dy is equal to 3x squared times dx. Okay, perfect. Now that means that we can actually evaluate dy to get a number because we've been given delta x and we've been given x. So if you remember from before, delta x is simply equal to dx. So that means that dx is equal to 0.1. And since we know that x is equal to 1, we can simply plug that in here. So dy is equal to 3 times 1 times 0.1. And that gives us 0.3. Wonderful. Okay, so now let's go ahead and evaluate delta y. So if you remember from before, our formula for delta y is going to be equal to f of x plus delta x, minus f of x. Okay, so in this scenario, we've got our x and we've got our delta x, so let's plug those in. Delta y is equal to f of 1 plus 0.1 minus f of x. So that would just be f of 1. So f of 1 is going to be 1 cubed, which is just 1. And f of 1.1 is going to be 1.1 cubed. And so let's use a calculator to evaluate what that is. So that would be 1.1 cubed minus 1 is equal to 0.331. Okay, so this would be the actual change in y on the function versus our approximation that we calculated up here. So as you can see, that's a pretty close approximation, and that illustrates why differentials can be an important tool when you don't have a calculator or something like that around. Okay, so let's recap what we've learned about differentials. dy is the differential of y, and the formula you can use to calculate dy is is equal to f prime of x times dx. Dx is equal to delta x, but dy is not equal to delta y. Dy is simply an approximation for delta y. The formula for delta y is f of x plus delta x minus f of x. Thank you so much for listening to our video about differentials and linear approximations. If you still need some help, you can come to our office hours, which are on December 2nd from 12 to 1, and you can complete our homework assignment, which has plenty more practice problems for you to go through. Thank you very much.